completely frozen. Something happened.
Yes, they're around for
Excellent. Yes. Finally. Excellent. Good morning, everyone. Today, on behalf of my collaborators, I'll talk about multi-arm bandits played by multiple agents, where all the agents are strategic. Let's start with a simplified example. Consider a bunch of agents who all are trying to estimate this oracle that gives you IID Gaussian samples with a hidden mean. Now, all these agents can repeatedly sample this oracle and have observations, and then share all these observations over a shared data pool for every agent to use for his final estimate. Each agent can see the shared data pool and what other agents are adding, but cannot observe what the other agents are privately interacting with the oracle, what they are sampling and observing from the oracle. Now, because nobody can see his private interaction, a self-interested agent might just not make that sampling work. He might not put in that effort because there is some cost associated with sampling or something, and might instead just report arbitrary values. And he might think he could just use the reported values of all the other agents for his final estimate. That's great. But what happens if every single agent thinks like this? What if every single agent wants to free ride off the efforts of others? Then everybody starts reporting arbitrary values, and then the entire estimation collapses. So to prevent self-interested agents from collapsing the learning this way, we could have a principal or an auditor who can see the shared data pool and what each agent is adding, but cannot see what the agents are privately interacting with the oracle and can't sample the oracle directly either. Surprisingly, this principle can still probabilistically catch an agent who is free riding. The main idea is as follows. He could compare what one agent is reporting versus what the other agents are reporting. And if the others are saying something close to 5 and 4, and if one agent is saying 42, then it's probably free riding. And then the principal could then levy a monetary penalty to that agent proportional to the deviation that his reported value has. Now, this is a very simplified illustration, but it gives the essence of what our problem is and what the algorithmic idea is. We consider a d-dimensional linear bandit setup faced by M agents who are selfish, which means they have their own objective to optimize. They are rational, they can compute the consequences of their actions and choose their strategy accordingly. And in this setup, they all want to minimize their personal regret. In the exploration versus exploitation trade-off that bandits are designed to handle, a selfish agent would exploit more and then want to use the shared data from other agents as exploration. So in our setting, the agent is strategic about two things: the action that he plays on the bandit instance, and how he reports the observed values. He could misreport the observed values from the bandit. So we put ourselves in the shoes of the principal and ask how we could incentivize these agents to instead minimize the social regret, the sum of regret of all the agents put together. And the principal can see the shared data pool, and with that he could then come up with a penalty that he can levy on different agents. So our main result is as follows. It is already known that in the single agent non-strategic case, where the agent minimizes the personal regret, d times square root of t regret is achievable by the linear CP algorithm. And when there are multiple such non-strategic agents, where the objective is to minimize the social regret, an enhancement of 1 over root m is also possible. That's also known. And we consider the multi-agent case where all the agents are strategic, where the objective goes back to being minimizing the personal regret plus the penalty that the principal can levy. And we show that d times square root of t over m regret bound is possible. So this shows that the regret with strategic agents and the regret without strategic agents is actually identical, despite the selfish nature of the agents and the divergent objectives. To achieve this result, We come up with a statistical test that the principal uses on the shared data pool and to decide the penalty for each agent. And we design a bandit algorithm that is a low switching variant of the linear CB algorithm, where the learning happens in a delayed and staggered manner. And we ask that the agent report the true values that they see. So our first result is that when principal follows his protocol A1 in common knowledge, then it is a Nash equilibrium for all agents to follow A2. Our second result is that when all the agents follow this A2, then the regret that I stated before actually is achievable. So we have some more contributions and insights about what the statistical test is and about the existence of other Nash equilibria in this game. But for all that, I would ask you to come to our poster number 7 and we can talk more about it. Thank you.
Question over there?
Yes.
Thanks, Sudhekar. I was wondering that the principle uses statistical test to
Yes.
detect if a selfish agent is not reporting back the true samples.
Yeah.
But if I'm a selfish agent, I might just say that, I might just think that, okay, I will see what the other agents are sharing, I will take an empirical average of that and report that back.
That's absolutely correct. So yes, so this is a multi-round interaction. So yes, a strategic agent could see what the other agents are reporting in the past and then use that and take an average. But the thing is, the statistical test is designed in a way such that as the rounds progress, the accuracy that the principal would expect from those reported samples would actually increase. So it's not just reporting the true values. I would want you to report the average of all the samples that you've seen so far and whatever you're currently observing from the bandit. So I would expect the variance to be so tight in the future, in the later rounds, so that unless you really keep on doing the work, you can't really escape the penalty just by looking at what the other agents were sharing in the past.
Can I have one more?
Sure.
Even the couple of agents can collaborate together to still fool the principal, even with the variance.
So not collaborate, they could collude together.
Yeah.
So even if they want to collude, that's where there is a notion of other Nash equilibrium. For example, if all the agents together decide to bias the reported estimate by some plus alpha, then everybody escapes the penalty, because the principal, without being able to sample the oracle himself, will have to just trust or compare one against the other, and everybody would escape the penalty. So there are some other Nash equilibrium, but that is necessarily not better for any of the agents. They are much better off reporting the true values.
Great, let's thank the speaker again.
Thank you.
Okay, last call for bandits for efficient